Okay, hello everyone. So I welcome you in this lecture of RB Tree Deletion. So I believe already you have gone through the algorithm of RB Tree Deletion. This is basically to do some practice on this deletion exercise. So we'll start with the one RB tree and then we will perform some operation or I can say deletion operation and see how it will work. So let's start. So first of all, just quickly have a look on the algorithm of RB tree deletion. So we have already discussed that in our previous video, we have discussed that it has certain possible cases when we do this deletion operation. So case one and case two is straightforward that you do the deletion and there is no need to worry about because it still maintains all the arbitrary properties. But then there is case three who have five variation you can say uh, that will create a scenario of double black. So double black is a scenario when you are going to delete a node which color is black, and because of this deletion, the black height property is not maintained, and then we need to do certain rotations to fix this uh, RB tree. Okay, so what we are going to do is first we will construct one RB tree. So already we have discussed how to construct RB tree using an insertion algorithm. We have already did the practice. So you can check my previous video of inserting a node in an arbitrary. So we constructed an arbitrary by inserting these nodes in a sequence 49, 28, 58, 14, 30. So I'm not doing it again. And this is what we get after inserting all these nodes. So this is our arbitrary. And now we are going to delete these nodes. So we are going to delete these five nodes with the keys given to us. So let's start and let me show you the screen that will also show us the algorithm so that we can be like cross check that that the step that we are doing is also as aligned with the algorithm of the arbitrary deletion. Okay, so let's have a look here. These are the steps of the algorithm given here. All the cases have been mentioned here for our reference, and this is the tree that we are working on, and we have to delete this. So the very first node to delete is with the key value 52. And let me remind you that when we do the arbitrary deletion, we have to go with the deletion as we are doing in a binary search tree. So this arbitrary is also a binary search tree, or you can say it's a balanced binary search tree. So we will be deleting initially with principle of BST, and then we will check that the resultant tree is the arbitrary or not. So we'll start with delete 52. 52, if you look at this, so these are the black color, red color, black color. This is 52. So when you delete this node, so if you look at this, this is a black color node, and we know that whenever any black color node is deleted, it will dilute the red, this black height property. So what we are going to do is we will just delete this key and we will place it as a double black node. That means double black node basically means that the tree is not maintaining the RB tree properties and we need to fix up. So we need to remove this double black and bring this tree back to its RB tree structure. So we'll get this thing. Let me write it here. 58. And then we have this is the right part. So I am just leaving this like a tree, and here we can see what will happen. And this is 52, which is going to become a double black, and this we need to remove. This double black need to be removed, and we will follow this algorithm to see what is to be done. So let me write the color as well. Okay, so these are the colors. Now if you look at this, this is the case where the sibling is black color and having the red child. So so I believe this is the case where the far child is red. Let us look to the cases. If the sibling is red, this is not applicable. If the sibling is black and both of child are black, this is not applicable. Now look at this. If the sibling is black and whose far from DB is black. Okay, so this is also not applicable because it says when the far child, this is your black node, means this is double black node, this is sibling, and this is the far child, this is the near child, and this must be black, which is not here. So we'll go to this case number 5, and this is a terminal case. Terminal case means we will apply this step, and we will find that this is again returned back to the RB tree structure. So we'll apply this. So I can write this, the case, this is applicable. I call it as a 3-5 case. So here what is required? Here the far child is red. Now this is the far child, right? So swap the color of the parent and sibling. So this is sibling and parent. These two need to be swap the colors and rotate the parent in DB direction. And this is the parent, and it has to be rotated in the DB direction. That is a double black. DB means double black. And remove DB, and this is to be removed, and change the color of the far child to black, and this is going to be convert to black. Okay, so what we get, let us draw here. So we get 30, and this black will become red, 28 becomes red, and 49 will becomes black, and 14 will be converted to black, and 30 will remain red. So if you look at this, uh, the black height, if you look at this in the tree, so every time when you perform any operation, you need to check that black height is maintained or not. So in the given tree, the black height is actually 1, 2, 2. Now in the resultant, what we have find the black height is 2 in this path, the black height is 2 in this path. So we assume that now this is also the root is black and the red node has a black child. So this is fulfilling the requirement. So we are done with deletion of 52. 28, the next to delete. So 28 is this. So let me make this tree. Now this means that this is a right subtree, which I am not again drawing here because it is not required. It will remain the same. So whenever we do deletion in the left hand side, it does not actually impact to the right hand side tree. Now the next to delete is 28. 28 to delete. So let me write here. This is for delete. So just recall how to insert and delete the node in a binary search tree. So whenever we have a node which has two child, we can either go for a predecessor or a successor method. Predecessor method, that means I will find the previous element of this key. So if I look for the previous node that comes before 28, that is 14. So I am going to replace this with 14. Okay, and then I need to uh, delete this one. Okay, so let me show you here what is happening. So I will write 58 here, this node to be deleted. So this is a black color node. So whenever we delete a black color node, we need to represent as a double black, means this deletion will impact the black height of this tree, and we need to fix this. Okay, so we are now going to look to our algorithm that how it is going to be fixed. So let us understand what is the scenario. Let me write the colors here. So I believe that you are aware that how to do deletion in a binary search tree. So I have replaced this key with the key which I want to delete, and then I will again recursively call the deletion algorithm to delete 14, and this is how we get here. So this is a scenario where you will find that the sibling is black in color and the near child is red. So if you look this case where the sibling child who is far from DB is black but near child is red. So far child, this is actually nil, which is black in color. So this is this case 3 4. So we are going to apply case 3 4. Now what is to be done in case 3 4? we will swap the color of the sibling and sibling child. So this and this node color to be swapped. Okay, and what is the color of 49? 49 color is black. Okay, this we have to swap. This is one thing. Rotate the sibling in opposite direction to DB. This sibling to be rotated in the opposite direction. This is DB direction and this is opposite to DB. So we'll rotate here. And then we will apply case 6. So if you remember when we were doing insertion in the RB tree, whenever there is a case 2, so case 2 will always result into case 3. Here also we have this kind of result. Whenever we apply this case 3, 4, then we definitely move to this one, right? So apply case 6, this is not case, this is apply case 3, 5. So whenever we apply this one, it will definitely take you to this one. Okay, so let's have a look here. So now let me do it here. So what is required? I need to fill 30, 49, and here we have double black. Now we are going to swap the colors. So this 30 is. Now if you look at this, it will make you or take you to the case 3, 5. Now what is this? Here we have double black. You can look to the sibling and sibling far child is red in color. So it's say here when D sibling is black and far child is red. So what is required? In this case, we are going to swap the color of parent and sibling. So the very first thing is let me write the colors here. This is red color. So first we have to swap this color of the two things, means the two nodes, and then rotate parent in the DB direction. This is parent. It has to be rotated in the DB direction. This is DB, so it has to rotate in this anti-clockwise direction and remove DB. And DB need to be removed and change the color of red. This color to be changed to black. So now let's see what we will get. And we have removed this node. So if you look at this, what are the status? So if you look at this, if you go check the uh, red black height, so here we have black height is 1 and 2 and 1 and 2, and already we have checked that in the right hand side also it is true. So we have get this structure as a RB tree structure. So we are done with the 28 deletion. Now 79. So 79, if you look, it comes in this side. So let me draw this part as well. So at this moment, this is a RB tree because the root is black, the red node has a black child, and the black height is having 2. Means the black height is 2 at all the path if you check. Okay, so now we have to delete 79. So 79 is this node which is red in color. So it will be deleted directly. So you can see here, if the node to be deleted is red, just delete it and it's a terminal case. That means there is nothing to worry about and our resultant tree is still a RB tree. So I just delete it from here itself and we are done with deletion of 79. Then next is 75. Now we have to delete this node. Okay. Now this is black in color. So whenever we delete a black color node, it will result into a double black because it is going to affect the black height of the tree. So let us see how to handle this tree. And this is going to become a double black. Let me write the colors. This is black. This is red. This is black. So now we'll see which case is actually here. So this is the case, I believe. So if we look into this, when DB sibling is black, so this is your DB double black, sibling is black, and both of our childs are black. So actually, we have no child here. That means we have a nil, and nil is considered as a black node. So this is case 3, 3. So here it says we are here. Remove the DB node. So we were going to remove this node. Okay, then add extra black to its parent. Now we are going to shift this actually, means if we remove this, then we are going sort of the black color. So in this stage, what we are going to do, we are going to shift this black to this, right? Now, if this is a red color node, then this becomes a single black. If it is already a black color, then it becomes double black. But you can say luckily or fortunately, this is a red color. So this is going to be converted into black color. And if parent is red, then make it black. If parent is black, then make it double black and make sibling red. and sibling to be make red color. So this sibling to be make a red color. So let's see what we will get. This is already a black. So if you look onto the means the resultant tree, is it a RB tree? So yes, there is no double black, and the black height is actually 2 here, and you can see this side is also 2 here. So that means we are getting the resultant tree as a RB tree. So we are done with 75 also is deleted. Now the last is 49 to delete. So let me draw this structure as well. So 30 and 14 and 49. This is red, this is black and black. So is this arbitrary? Yes. Let me cross check. This is root is black. Red node has a black child. The black height is 2 here. Black height is 2 here. Black height is 2 here. This is actually fulfilling the arbitrary property. Now the last to delete is 49, and 49 is here, which is again a black. So it is again going to make a double black. So let me draw the structure. This is to delete 49, it becomes double black. So this is black color. This is 30 red color, and this is black color. So again, if you look at this, this is case number 3, I guess, because uh, sibling is black and the childs are also black. So that means this nil nodes are also black. So this is actually case 3. So we have to shift this. We have to remove this black and double black, and this is going to shift to the parent. This is what we have seen in the algorithm. And if the parent is red, it becomes a black. So this is going to become a black, and this if the red it is going to become a black. If it is black, it becomes double black. This is not applicable, and sibling becoming red. So this sibling becoming the red. So let me see what is the output. So we'll get 58, and this becomes 30. This is 30, and this is 14. This becomes black. This becomes red, and this is black. And we are done. Let me draw the complete tree. So this is what 67, 63, and we are left with B, and this is R. So this is our final tree, and let's us check is it a arbitrary or not. So this is 58. This is black, and we have black height property satisfied, and also satisfied that red node has a black child. Okay, done. So this is our final tree, and we are done with this. So I hope you have understood how to apply uh, these steps for arbitrary deletion. So let's do more examples in the next video. Thank you very much.